Hello and welcome everyone to this third lecture on electromagnetic waves. In today's lecture, we will learn about the nature of electromagnetic waves, and needless to say that this lecture is going to be a little bit mathematical in nature. Alright, because we will be analyzing the wave equation, the equation corresponding to electric field and magnetic field, and we will see how the velocity of waves can be derived, not in a sense derived, but actually can be stated. Okay, so let's start. Now, nature of electromagnetic waves, the other day in a different lecture, I already told you that electromagnetic wave is nothing but it's an oscillating electric and magnetic field. So, you can see in the vertical direction, we have an oscillating electric field, and in the horizontal direction, we have an oscillating magnetic field, and ultimately the wave is coming in the z direction. Now, naturally, the wavelength, as you all know, that crest to crest or trough to trough, that distance is known as the wavelength. So, here also that particular thing never makes a variation. So, wavelength happens to be either the crest to crest distance of the electric field oscillation or the magnetic field oscillation. Now, in this case, one thing is important to remember, that wherever or at what time the electric field attains a maximum, the magnetic field also attains the maximum simultaneously. Their direction or the plans are different, but the attainment time of maxima or the minima happens to be the same. All right. So, the electric and the magnetic field are perpendicular to each other in an electromagnetic wave and to the direction of propagation. So, this picture is very well defining or giving a clear picture of this particular fact, that electric and magnetic field in an electromagnetic wave are perpendicular to each other, and not only that, both of them are also perpendicular to the direction of propagation. So, here I have chosen my axis as x, y and z. This is completely based on my wish. You can also have your own choice. For example, you could have coined these particular axis to be y, this to be x, like that. Now, let us consider a plane electromagnetic wave propagating along z direction. The electric field is oscillating along x and the magnetic field is oscillating along y. Both of these fields are the functions of space coordinate z and the time. So, if I have to write, in that case, how would I write? Suppose this is my electric field E. In that case, I will write it as a function of z and x, z and t. Means it will be a function of position and time, because this is a wave equation. But position, which position? Z, because the electric field is varying along z. Alright, it is oscillating along y, but it is the wave, since the wave is coming along z, hence electric field will be obtained at different values of z. Similarly, the magnetic field will also be a function of z and t. Got it? So that's what we have written over here, that both these fields, that is electric and magnetic fields, are function of the space coordinate z and the time. Thus we can write Ex, because I have written the electric field to be Ex. Why? Because it is oscillating along x. So, in order to differentiate that particular thing, or in order to distinguish the electric field in terms of its oscillation axis, I have given a suffix x. So, Ex happens to be equal to E naught, which is the amplitude of the field variation, then sine of kz minus omega t. And similarly, By, because y is the direction in which the magnetic field is varying, so that By becomes equal to B naught sine of kz minus omega t. Now, E naught and B naught are the amplitudes of oscillation. Okay, so these are the equations. Actually, these are the solutions of electric and magnetic field, but otherwise they frame their own differential equation, or rather partial differential equation of electric field and magnetic field. That's what we get. So now we have these two expressions here. This k is known as the wave vector, or rather the magnitude of the wave vector, or the propagation vector k. Now, what is a propagation vector? It's a vector which describes the direction of the propagation of the wave, and omega is the angular frequency of oscillation. All right. Now, note that k happens to be equal to twice pi by lambda. Now, when we are talking about the wave chapter on waves, then also we have come across these terminologies, that what is a wave vector, how is it related to the wavelength lambda, and there we have come to know already that k is equal to twice pi by lambda. Now, the same definition happens even in the case of electromagnetic wave. Although in the wave chapter we talked about the mechanical waves by and large, but here we are talking about electromagnetic wave, but the definitions remain the same. Alright. Now the velocity of the wave is given by c equal to omega upon k. That means the ratio of the angular frequency to the wave vector. Now it so happens that this c, which is the velocity of the light or the velocity of the electromagnetic wave, that can also be written as 1 upon square root of mu naught epsilon naught. Now this is a derivation, is a result of a derivation, okay, but that framing or that derivation is not required or beyond the scope of your syllabus. So that is why you just have to remember that c can either be written as the ratio of omega by k, or it can also be written as a ratio of 1 upon square root of mu naught epsilon naught, where mu naught is the absolute permeability of free space, epsilon naught is the absolute permittivity of this free space. Now we know the values of mu naught and epsilon naught to be this. If you put it back to this equation and just calculate, to your strange you will get the value to be around 3 times 10 to the power 8 meter per second. Now we are very familiar with this number. What this number is nothing but the speed of light in vacuum. Now since we are analyzing all our analysis, whatever we are doing right now, we are doing it for the vacuum only. How is it sure that we are doing it for vacuum? Because we have applied here see mu naught and epsilon naught. Provided I had to go for a material medium, in that case I could not write mu naught or epsilon naught. I would have written at that time as mu and epsilon. Okay. Now we can also prove that C is equal to nu lambda. Now this is a result which we all know from our high school lessons. C is equal to nu lambda. Now how does it appear? C is equal to nu lambda appear from this particular relation itself, because omega equal to twice pi nu, k is equal to twice pi by lambda. If you take this ratio, this twice pi and twice pi gets cancelled, lambda goes up, it becomes nu lambda. Alright. So up to this it is very much clear, I hope. There is one thing which is new to you right now, that is, it can also be seen from the Maxwell's equation that the magnitude of the electric and the magnetic fields in an electromagnetic waves are related as B naught equal to E naught upon C. That means the amplitudes you talked about here, because electric field and the magnetic field, these are constantly varying both with time and space z. Okay, but the amplitudes which are only the function of space coordinate, that are related for the case of electric and magnetic field by this equation, that B naught equal to E naught upon C. Now this relation is a very important relation, because you will have lot of numerical problem based on this relation. Okay. Now up till now we have talked about the electromagnetic waves in space, empty space. That means empty space in the sense wherever there is a vacuum. What happens now? Let us discuss what happens whenever the electromagnetic wave passes through a material medium. It could be either a glass, it could be water, it could be any substance which is either transparent or maybe opaque, because if it is an opaque, it will anyway stop the flow of electromagnetic wave through it. Okay, but there is also a glitch, or there is also a point to be noted in this case, that opaque for one sort of electromagnetic wave may not be opaque for another sort of electromagnetic wave. For example, if you have a wall, now a wall is opaque to the visible rays, isn't it? Because if you make a torch across the wall, in that case the light will not pass. But if you have a radio wave, which is also a part of the electromagnetic spectrum, or which is also an electromagnetic wave, that can easily pass through the wall, because otherwise you would not have heard your radio signals. Okay, because we normally keep our radio receiver within the house and we very well receive the signal. So how come the radio waves come from the transmission station? It comes because it never gets attenuated by the presence of the buildings or by the presence of the trees, houses, etc. That means it can easily pass through them. Similarly, you have got infrared or microwaves which can also pass through. But so it's a visible ray or maybe sometimes ultraviolet, they cannot pass through these kind of opaque substances. So opaque is a term which is very much specific to a class of electromagnetic wave. Something which is opaque to visible range of electromagnetic wave may not be opaque to the other, for example, radio waves or infrared, right? So now let us try to understand what happens whenever the electromagnetic waves passes through a material medium. So as we know, the electromagnetic waves do not require any material medium to pass through. Okay. Now there is a difference in these statements. Electromagnetic waves do not require any material medium to pass through, but that doesn't mean that it doesn't interact with the material medium. Okay, it interacts because while it passes in our world, it interacts with many different objects which tries to obstruct its motion. So that is why it doesn't require the support of material medium, but it necessarily and certainly interacts with the material medium. So however, very often they encounter material medium in their journey. For example, light often passes through the glass medium. In such a case, the velocity of the electromagnetic waves are different than c. Now remember, in the previous slide I have used c, letter c, or small c rather, to designate or to denote the velocity of the electromagnetic waves. Now in this case, c is the velocity of electromagnetic wave in vacuum, which we have got it to be somewhere around 3 times 10 to the power 8 meter per second. But whenever the electromagnetic wave comes inside the material medium, its velocity decreases. Alright, it is less than c. And if eta, this symbol is known as eta, be the refractive index of the medium, then the velocity of the electromagnetic wave is eta is equal to c upon v. Now let me write the symbol name because by pronunciation this may not be very clear. I am calling this to be eta, E T A. All right. So eta, the refractive index of the material, is equal to c by v. Now certainly you can see, suppose if electromagnetic wave is passing through glass. Now what we know, for a glass medium, what is the eta? The glassy medium eta is equal to 1.5. Now since this is a refractive index, it is a dimensionless constant. It doesn't have any dimension. So what happens, the velocity? Then velocity will be c upon eta. C is equal to 3 times 10 to the power 8 divided by 1.5. So that happens to be around 1.5, because 3 divided by 1.5 is how much? 3 divided by 1.5, sorry, that's 2 times 10 to the power 8 meter per second. So whenever the light travels through a material medium like glass, whose refractive index is 1.5, in that case you have the velocity to be 2 times 10 to the power 8 meter per second, which is not 3 into 10 to the power 8. So it has certainly reduced from that. Got it? So similarly for water also you can calculate, because refractive index is 1.33. So you can calculate the velocity of electromagnetic wave or velocity of light in water, because you just have to divide it by 3 into 10 to the power 8 by 1.33 in that case. Okay. Now here v is the velocity of light in the material medium. Now how you can write, because c, you remember we wrote about c is equal to we wrote like this, mu naught epsilon naught, and there already I told that c is, since the velocity of light in vacuum, I have written the parameters of the vacuum. But since now v is the velocity of the light in material medium, I have to write the parameters of material medium. So I have to replace mu naught and epsilon naught by mu and epsilon, where mu and epsilon are the permeability and permittivity of the concerned medium. Now that itself means what? That itself means that velocity of light depends on the electric and magnetic properties of the medium, because one is the permeability, which is a magnetic property, and epsilon naught is the electric permittivity of the medium. So the velocity of light always depends on the electric and magnetic properties of the medium. This is a very important statement which you should remember. Now let's talk about a prism, and we all have seen this particular phenomena which is called dispersion. Whenever a white light passes through a prism, it gets dispersed into different colors, several colors for example. If it is a white light, it will be dispersed into 7 colors. Uh, so, uh, in that case, what do you see? The dispersion through prism occurs because different components of light travels at different velocities through the medium. What happens actually when you will go through dispersion, you will come to know that the dispersion of the prism occurs because the refractive index of the medium appears to be different for different colors. For example, the refractive index for the violet as it appears for the material of the prism is not the same for that of the red component. And if the refractive index is different, that itself means the velocity of the components are different. So the velocity with which the red light travels inside the prism is not exactly equal to the velocity at which the violet component or the yellow component or the green component of light travels within the medium. So their velocities are different. Refractive index difference means there is a velocity difference also because they are related, as we can see. So ultimately what happens, different colors emerges out of the material medium like prism at different times, and this gives rise to the deviation, and ultimately the phenomena is known as dispersion. All right, so you understand that this is a very important thing. This has an important consequence in fiber optic communication also. In fiber optic communication, we use a fiber. For example, the internet, high speed internet nowadays you are using in uh, broadband connections. There we use fibers, optical fibers. So in the design of the optical fiber, you have to take into consideration this phenomena of dispersion, right, for greater and good transmission of signals. So that's beyond the scope of this particular topic, but sometime if we get time, we can make another session or a video on that. So these are some of the important points which you have to remember about the electromagnetic waves. I have written these points to be the same exactly what we have discussed till now. I just request you to go through this particular slide very well. Okay, so it need not to be explained in this case because we already have learned about this point in a greater detail. This is just summarizing kind of a thing. Okay, so let's move on. Now there is a question: show that electromagnetic energy or the energy in the electromagnetic wave is equally divided between the electric field and the magnetic field. Now this is a very important question. That means what? That whatever energy, now first question is, does the electromagnetic wave carry any energy? Answer is yes, it does carry an energy. Now if it carries an energy, then how the energy is divided between electric component and magnetic component? Because we know that electromagnetic wave, it sustains itself. How? Because first we create an oscillating electric field, that oscillating electric field gives rise to an oscillating magnetic field, an oscillating magnetic field can give rise to a oscillating electric field, and like that it goes on and on and on, and they self sustain, means the oscillation of electric field sustains the oscillation of magnetic field, and the oscillations of magnetic field sustains the oscillation of electric field. So they maintain each other. That means it has clearly two components, one is an electric, another is magnetic. So if the energy of electromagnetic wave I have to talk about, then I have to talk about the contributions of the electric and magnetic energies also. So the question is how they are divided into the electric and magnetic component, how the energy is split between electric and the magnetic component. That is what is the question. All right. So in order to answer that, let us individually understand the electric contribution and the magnetic contribution. So the uh, average electric energy density in vacuum is given by UE, which is equal to half of epsilon naught E square. Now this is something that you have to remember. By the way, this E which I have written here, this is nothing but E RMS, the root mean square value of the E, because electric field continues to vary. So which E we have to consider here is the RMS value of the electric field. Now we know that RMS value of electric field is nothing but the maximum value divided by square root of 2. Okay, because we already have encountered it in our alternating circuit, alternating current, that how to find RMS. RMS is always the maximum divided by the square root of 2. So ue is equal to half of epsilon naught E naught by square root of 2 whole square, or we get 1/4 of epsilon naught E naught square. This is the energy or the average energy from the electric component. Similarly, the average energy from the magnetic component is given by UB, that's equal to B square upon twice mu naught. Now these two things actually you have to remember. These are two new expressions, but you have to remember. We have not derived in our course, but please do remember them. So UB, what you can write, similarly this is also a B, means B RMS. You have to convert it, so B naught by square root of 2 whole square divided by twice mu naught, and ultimately you get it as B naught square by 4 mu naught. But there is a small modification that I have wrongly written it to be E, this should be B. Okay, this should be UB. Alright. Now similarly, so we have already got the electric contribution to the average energy and magnetic contribution to the average energy. Now let's see how they are related. So UE is equal to 1/4 of epsilon naught E naught square. Already I have written that, this expression itself I have written here. So 1/4 of epsilon naught, because electric field amplitude and the magnetic field amplitude are related as B naught equal to E naught by C. So E naught happens to be C B naught, so which I have written here. So this becomes 1 upon epsilon 1 upon 4 epsilon naught C square B naught square. Now C square means what? Because C means, already we know, square root of mu naught epsilon naught. So if I write C square, that becomes 1 upon mu naught epsilon naught. So that is why I have written in place of C square mu naught epsilon naught, this particular term. And this epsilon naught comes here, B naught square comes here. So what ultimately you get, that epsilon naught gets cancelled, and you remain with B naught square by 4 mu naught, B naught square by 4 mu naught. So electric field component, the average energy due to electric field is equal to the average energy due to magnetic component, because this is nothing but the magnetic component UB. So I see that the electric and the magnetic field averages are exactly the same. So that is why, what is the total average energy density? That will be equal to sum total of the electric component and magnetic component, but since UB is equal to UE, I can write it to be twice UE, which is equal to half of epsilon naught E naught square. Actually UE is equal to 1/4 of epsilon naught E naught square, but 1/4 and this 2 gets cancelled, so you remain with half epsilon naught E naught square. Then U average, you can also write it in terms of magnetic contribution. So in terms of magnetic contribution, I will write it as twice UB, which happens to be B is naught square by twice mu naught. You can either write this or you can write this. Okay, it can be, the question can be asked either in from the perspective of a magnetic field component or from the perspective of an electric field component. But remember, the contribution to the average energy both from the electric and the magnetic field are the same. That is why UE is equal to UB. Okay, so that's a very important consequence. We have learned about the energy of electromagnetic waves. There is one more thing, that's the intensity of electromagnetic waves, and that's a very important thing. What is the intensity definition? Intensity of electromagnetic wave is defined as the energy crossing per unit area per second perpendicular to the direction of propagation of electromagnetic wave. Now for example, let us consider a cylindrical volume through which electromagnetic wave is going. Now the cylinder has got an area of cross section A as shown here. Okay, so this length is then C delta t, because the wave is traveling at C, speed C. So since I have considered the speed to be C, that itself means that I have considered it to be vacuum. So this point is P, this point is Q. Electromagnetic waves are entering through this particular end and getting exit through this point. So what we get, the total energy of the electromagnetic wave is nothing but the average energy density. Remember, UF is equal to average energy density, that means energy per unit volume. So since it is energy per unit volume, if you product with another volume, the volume will get cancelled, you remain with energy. So capital U, which I have written here, this shows the total energy of the electromagnetic wave, not energy density, but U average is the energy density. Okay, so that is why I have to multiply a volume. area into distance, that is what is a volume. So if I do that, in that case, by the definition of intensity, I get intensity is equal to U upon AT, isn't it? Because the intensity means total electromagnetic energy divided by the area and time. So that itself means U means UF A C delta T. So if you do that, you will get ultimately U average into C. But U average equal to half of epsilon naught E naught square, already we have got from previous slide. If you put it back, then you get these two relation. This is in terms of electric component. So this is intensity in terms of electric component, and this is the same expression of intensity of electromagnetic wave in terms of magnetic component. Okay, the things are very easy. If you have any doubt or question, please do ask. Next, there is another slide. This is the last slide of today's discussion. The momentum. There is an interesting point, whether electromagnetic wave can have momentum. The answer is yes. The linear momentum of the electromagnetic wave is rather expressed as P is equal to U upon C. What is U? The electromagnetic energy divided by the velocity at which the ray or the wave is traveling in space. So if the electromagnetic wave is completely absorbed by a surface, then it delivers the energy U and momentum U by C to the surface. That's a very important point you should remember. If the electromagnetic energy is absorbed completely, it delivers a momentum U upon C. The complete momentum is being delivered. But if the wave is reflected, then there is a change of momentum which is twice U by C, which is imparted onto the surface. Because it reflects means what? The momentum changes from P to minus P. So total change of momentum happens to be P minus of minus P, that is equal to twice P. So that becomes equal to twice U upon C. Alright. So therefore electromagnetic waves exerts a force on the surface incidence, because it transfers momentum, means momentum transfer per unit time is what is known as a force by Newton's second law. So that is why if it transfers momentum, or if it is capable of transferring momentum onto the surface on which it incidents, that means it can transfer some force on it, exert some force on it. Am I clear? So that's the end of this particular lecture. Today we have understood the very nature and different aspects of electromagnetic waves. The things are a little bit mathematical, although not very mathematical, but you need to go and watch at the videos concentrately. Okay, so please do concentrate on these things and very carefully and with deep interest, please go through this topic. Okay, so in the next class we will talk about various classes of electromagnetic waves, how they do interact with matter, and all these aspects. Okay, thank you so much.